going live.
Okay.
Morning, guys. How's it going? Are we ready to start? Did you have a good weekend? Learn anything new? We ready to go? Alright, let me grab a new marker to start. Hey guys, hey guys. Morning, Lucas. Good morning. Kelsey, hey, and Kara. Hey, Eve. Howdy, howdy. Just 2 more weeks, guys. 2 more weeks. We got this. We got this. Hey, Zoe. Hey, Priscilla. Morning, morning. Up and at 'em this Monday morning. We're going to do some normal curve today. Start talking about the normal distribution. Our bell-shaped curve. Hey, Bo. So, how about we go ahead and get started? Hope y'all enjoyed the Bayes theorem last week. I always love Bayes theorem. It's always good and interesting. Hey, Imani. Now, I don't want y'all to think that the tests aren't good. The tests are good. So if you have a disease, most of the time it's going to catch that you have the disease. If you don't have the disease, most of the time it's going to say you don't have the disease. I know it's kind of paradoxical. It's kind of like weird because if I get a positive test, it's not an 80% or a 90% or a 95% chance that I have it. So a lot of you on the assessment of it told me that Charlotte still had an 80% chance of having the disease. But once she found out she was positive, she went into a different group. That 80% is if she has the disease and she gets a positive, then it shows that 80% of the time. But when I walk away with that breast cancer positive test, or she walked away with a positive for Down syndrome, at that moment, the percent chance that she actually had Down syndrome was just 4%. It was only 4%. Only 4% of those parents that get a positive there actually have a child who has Down syndrome. So just because the tests are good, don't think that they're bad. It's just that because the disease doesn't show up as often, 1% of a larger number is a large number. I don't know if that made any sense. Yeah. I got a lot of people who were confused still by the Bayes theorem, and I know it is kind of confusing. But you know, if I do 100% of these people get caught, and there's only 80 of them, or 100, let's just make it 100, and all of them get caught that they have the disease. But then I've got, 10,000 people over here who don't have the disease. And if just 1% of them If just 1% of them, you know, are told that they have the disease, well, that's such a big number that 1% of it, that's 100 people that end up thinking they have the disease even though they don't. So, you know, then if I walk away with a positive test, well, only 200 people walked away with a positive test. So even though it was really good, 99% of the time it said they don't have the disease, and 100% of the time that they do have the disease, it said they do have the disease, it's still, when you walk away with a test, 50% of the time that you have a positive test, you don't actually have the disease. And it has to do with the fact that not having the disease, if that number is large, then when I take even just 1% of it, it can be just as big as the numbers that we started with that had it. So yeah, as Mr. Simpson said, testing is powerful. It's important that we do the tests, and it can catch it. So I'll go in every year and do the stupid mammogram, and they'll go in and tell me that yes, it's positive, and I'll go back and do the ultrasound, and then they'll say negative. But I'm going to go in there and do it every year, because if I do end up with breast cancer, it's going to catch it. And then I go in for the ultrasound, and it's going to catch it. And I want to catch it. So it's just that sometimes I'm going to get those false positives. So the moral to the story is not that testing is bad. I don't want that to be the moral to last week. Testing is not bad. It's not the moral to the story. The moral to the story is, just because you get a positive test doesn't mean that you should start making life changes immediately. More testing is needed. So, I don't know if that made a difference or not. And that it's hard to get your mind wrapped around some numbers. I post on D2L a little Simpson's paradox, not named after us, don't we wish, but it is. It's Simpson's paradox, a little video of that's kind of like that base thinking. And I also put it on D2L, just on our Twitter little area. That's that same idea that it's kind of hard to get your mind wrapped around the numbers sometimes. Okay, let's talk normal curve. So somebody told me the answer. I think Priscilla already told me the answer to this. The mean score of an insurance commission licensure examination is 75 with a standard deviation of 5. The insurance commission can expect at least 75% of those taking the exam to score between what two numbers? And I think Priscilla already told me between 65 and 85. We know, based on Chevychev's, that no matter what the shape of this distribution is, you know, maybe the shape of that distribution is something like this. Or maybe when you look at the scores, you know, most people score here, a few people score really high, or maybe most people score really high and a few people score really low. So maybe the shape of the data looks like that. Whatever the shape of the data is, we know from Chevychev's that at least 75% of your data is exactly, Imani, 2 standard deviations from the mean. So I know that at least 75% of my data, no matter which shape it is, if my mean is at 75, and I go out 2 standard deviations, 80, 85, and back 70, 75. I count my 5s because that's my standard deviation. If I go up back 2 standard deviations, I know at least 75% of my data is within that 2 standard deviations. Okay, today we're going to learn about the normal curve. And with the normal curve, we can get even more exact than that. So here your answers are between 75 and 85. So 2 standard deviations out. You remember that? Today we're going to get even more exact when we have a symmetric or a normal shape to it. So let me just start by telling you about the normal distribution. We're going to do today a few things. That's a nice review. At least 75%. At least, says Terry Chest. Okay, so we're going to do these things today. First thing we're going to do is we are going to remember that probability and area are related. You remember that? That if I draw this spinner and I say, what's the probability you win? What you are doing is you are looking at the area of that circle to determine the probability. You're saying that the win takes up 1/4 of it. So the probability I win is 1/4. Or when we drew out our symmetric sample space, we could look at the area of that symmetric sample space to find our probabilities. So this is a big deal, that probability and area are related. Okay, that's number 1. All right, number 2. We're going to do a little bit of college algebra. So I'm going to do good, ain't Kara? I'm going to do a little bit of college algebra. Don't panic. And I'm going to do this college algebra just to kind of give us a feel for the shape that we're going to be dealing with. So this function, this is a function, and in college algebra we might graph this function. So I'm going to graph this function. I'm going to make an XY table, and I'm just going to plug in or substitute in some values for X and find out what my Y is equal to. So this is just a fancy way of saying Y. So I know. It'll be okay. I'm going to plug in an X value, and we're going to spit out a Y value. Okay? All right, and then we'll graph those points. So like if I put in a 0 for X, if I put in 0 for X, that's all it says is I'm going to put in 0 for X. 0 squared plus 1 is 0 plus 1 is 1. Hey, that's just equal to 1. So there's going to be a point on this graph at 0, 1. So let me do some graphing. We'll give you a short college algebra lesson. This is all college algebra is graphing, 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 graphing. You got it. Put in 0, out pops 1. I'm going to make my 1 pretty big. So there's a point. I don't walk any. That's what this says. Don't walk on the line any. And just climb up 1. Then I'm going to put in, let's put in 1. So if I substitute in 1 instead of 0, put in 1 instead of 0, what do I get out? Well, the top still stays 1. 1 squared is 1, plus 1 makes 2. So if I substitute in 1 for my x, I get out 1/2. So again, I'm going to plot this point. I'm going to go over 1 spot and up 1/2. So over 1 and up 1/2. And there's a point there. Great, great, great. All right, now let's substitute in 2. So I'm going to put in 2, put in 2. So here, the 1 stays 1, but 2 squared is 4. 4 plus 1 is 5. So I get out 1/5. Yeah, it's a good, so if that's 1/2, if that's 1/2, I'm going over 2 on my x. 1, 2 on my x. I'm only going up 1/5. You know, that's less than 1/2. So about there. Good, and Kara? So I went over 2 spots and up 1/5. I went over 1 spot and up 1/2. So right now, this part of my graph is looking something like this. And I just want to see if I go way out here, what happens? Like, what if my x were 10? What if I picked a big number for 10, for x? You know, like, I went way out here to 10. What would be happening? Well, if I put in 10 down there, 10 squared is 100. 100 plus 1 is 101. Notice that my fraction's getting little. Got this little bitty fraction. So the further out I go, I'm getting smaller and smaller and smaller and smaller and smaller and smaller. And in fact, what if I put in 100? Well, 100 squared would be with 4 zeros. So 10,000. 10,000 plus 1 is 10,001. So it's even smaller. So the further I go out, I get tinier and tinier. But I'm never going to make it down to 0. I'm never going to get this output of 0. We call that asymptotic behavior. It's getting closer and closer to 0, but it's not making it. Yay, I'll teach you a little college algebra along the way. It's not too bad. College algebra is not all that. Okay, then I'm going to go backwards. I want to look at what's happening on this side of the graph. Okay, so I'm going to plug in numbers for this side. So I'm going to put in -1 for my x, and I'm going to see what I get out. If I insert -1 for my x, -1 squared, well, -1 squared is equal to 1. 1 plus 1 is still 2. Notice when I put in that -1, because this squares it, I just end up with the same thing I ended up on the other side. I ended up with 1/2 again. So when I put in -1, I go up 1/2. I get a point on the other side. So if I had folded it on this axis, this point and that point would match one another. We say they're symmetric. They match one another. That's right. I am prepping you for taking me for college algebra in the fall. That's exactly right, Monty. Y'all gonna sign up for me for? You know you're loving the math. And yes, Bo, it mirrors. That's exactly right. So if I put a -2 in there, just by looking, I think I'm going to get out that 1/5. You know, if it really does mirror, I should get out that 1/5. Well, let's do it. Put in that -2. -2 squared is 4. 4 plus 1 is 5. Sure enough, I get out that 1/5. So it really does mirror. And so the smaller a number I put in for x, again, I'm going to get this teeny little bitty fraction out. But it's never going to make it to 0. Again, we call this asymptotic behavior. I'm going to write it down. This is an asymptote, where it's getting closer and closer to it, but never reaches it. It's an asymptote. Like that. Now, this particular function is not our normal curve, but it looks a lot like it. This is very, very, very similar. In that, when we talk about the normal curve here in a little bit, I'll explain a little more about it. When I talk about it, it's going to have this same symmetric shape, where this side mirrors the other side. And notice, remember when we talked about the shape of a distribution? The mean is going to be right here in the middle, but so are the median and the mode. So if I were to have a distribution of data that looked like that, my mean, my median, and my mode are right there in the middle. Tad bit bigger. I sure can. I sure will. I will. I'll write bigger. So the mean, the median, and the mode are all right here in the middle. And then it has this asymptotic behavior. So this college algebra idea is just to show you when we talk about the normal curve, this is the type of thing we're dealing with, where we have some function And it just so happens that the function is going to look like this picture. It's going to look similar to this picture. Okay, now I'm going to jump to even further in math, because now I'm going to jump to calculus. And here's what you need to know about this calculus. I'm going to teach you a little calculus, just a little. Okay, so, you know, we find the area of a rectangle. We do like length times width, and we find the area of the rectangle. I know, right? In calculus, what we learn to do is we learn to find the area under curves like this, or under pieces of curves. You know, maybe I want to find out the area between here and here. Maybe I want to find out that area. I can find out the area under the curve. Yeah. I can find out the area under the curve using this thing called an integral. So, by the way, if you ever look at our Simpson math, it has that fancy S. It's an integral symbol. And then the M, of course, for math is a mu symbol. Y'all know the mu from statistics, and then that integral comes from the calculus. So anyway, if I were to find the area underneath this curve, we do some fancy symbols there, and I get it for the whole curve, not just for a piece of it, but if I found the area under this entire curve, so from negative infinity to positive infinity, if I did that whole thing, it turns out that the area under that curve is pi. Who knew? So, fun stuff. Okay, so that's what we do in calculus, is we find out the area under the curve. It's one of the things we do anyway in calculus. Okay, with all that knowledge, when we have something called a probability density function, a probability density function, the area under that curve is always going to be equal to 1. Just like when we built our distributions, our probability distributions, they added up to be 1. When we have a probability density function, when we have this distribution, it's going to be okay, Aunt Kara. It'll be okay. I'm doing a lot of background, and then I'm going to make it simple. All right? It's going to be okay. It's going to be okay. Okay, so the area under the curve is going to be equal to 1. So I want you to picture this. The function I did happened to be pi, but I want you to picture this and pretend that the area under it is equal to 1. So that if I grab a piece of data from anywhere in that distribution, the whole thing, all of the data within that distribution would add up to 100% of it. Okay, so I'm going to teach you about a special probability density function. By the way, we just call these PDFs. Not the same PDFs that I asked you to put it in format for me to turn in. But a probability density function is also known as a PDF. And I'm going to teach you about a special one called the normal distribution, or the Gaussian curve. Okay? The Gaussian curve. I think I've told them about pi before, Mr. Simpson. I think that we've even talked about how the circle, how if we measure the diameter, and then we take that diameter and we put it around the circle, it'll take 3 and a little bit of them. I think I told them about doing that when we talked. Oh, maybe not. Because we didn't do Poisson in here, so maybe I didn't do it. Did I tell you all about that? I don't know if I did or not. A later date. Anyway, okay, so probability density function. I'm going to teach you a special one called the normal curve. And this function's going to look really scary, but it's going to be okay. just as I've done in the past. I'll make it be okay. This is part of it. This is the beginning. We've got this function notation, just like we did in algebra, where I have 1 over the square root of 2, where 2 is just some number, times pi, which is just some number. It's the number 3.14-ish. It's actually, you take 3 of these diameters and you can wrap it around the circle and there'll be a little bit left. That always works. So if I take this clock and I measure the diameter of it, and then I take that diameter, it's going to take 3 of those diameters and just a little bit every single time. Or if I take my coffee cup and I measure the diameter, it's going to take 3 of those little diameters and a little bit more every single time. So, you know, those of you with kids at home and you're sitting around bored and you want to entertain them, go have them find a circle, get some string, measure the diameter, and see how many of those little pieces of yarn that are the diameter width it takes to go around the circle. And do that with a bunch of different circles. And every single time it's going to take 3 and a little bit of them. Okay, so that's our pi. Pi is just a number. You know that symbol. That's our standard deviation. Or since it's squared, maybe you say it's the variance. So that's our standard deviation, or our, squared, or maybe you say that's your variance. Then that's all being multiplied by another constant. This is another constant called E. And E is approximately, he's a cousin of pi's in that he's another irrational number. He's 2.7182818284599045, blah, blah, blah. It goes on and on forever. Just like pi, is that 3.14, blah, 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 blah. This is E. It's just a number, though. This is just a number, that's just a number, this is just a number. So right now I just have my standard deviation. This E is being raised to a crazy exponent. It's negative of x minus the mean squared over 2 times the standard deviation squared. Or again, you could say the variance. Okay, look, don't panic. You're not going to have to know this formula, okay? I'm just showing you this function. And the reason I'm showing you this is I want you to realize that this probability density function, this normal distribution, if I were to go about graphing it, would look something like this. The distribution, that function would look something like that. And the area underneath this entire curve would equal 1. Okay. Whew. And it is reliant. It has a couple of little variables in it. It changes based upon the standard deviation and the mean of that particular function. So there is some differences in the shape. Sometimes it's taller and skinnier. Sometimes it's flatter and shorter, based upon that mean and that standard deviation. But it has this basic shape every single time, and the area under that curve is always going to be equal to 1. All right. So that was a lot of information just to overwhelm you. Now let me get to the part where we can actually look at some things. Okay, so somebody came along and they knew some calculus, and they said, let me just find the area under parts of the curve. What if I look at, now with our normal, you know your mean, your median, and your mode are about in the middle. So you know your mean is just, right about here in the middle. And each one of these little distances away, a standard deviation is just a distance away. We've drawn this kind of thing before. So, if my standard deviation is 1, if that were my standard deviation, if my standard deviation is 1, then this would be 1 standard deviation above my mean. This would be 2 standard deviations above my mean. And the same way backwards. So -1 and -2, well, this is 1 standard deviation below the mean. This is 1 standard deviation, 2 standard deviations below the mean. And we know from Chevychev's that at least 75% of our data is within here. But now that we have this function that we know the area is equal to 1, we can actually do some calculus to find out more specifically when we have this particular curve, the area. And so we don't have to do the calculus. Somebody's already done it for us. And they found out that the area from -1, so 1 standard deviation below the mean, to 1 standard deviation above the mean, this area of my curve is equal to 0.68. So the area from 1 standard deviation from the mean is 0.68, which y'all know that 0.68 is really equal to 68%. Those two things are the same thing. This decimal, 0.68, 68 hundredths, is equal to 68%. Decimals and percents, out to the hundredths place, this decimal is the same as that percent. This percent sign just means out of 100. So 68 hundredths is the same as 68 hundredths. Okay, so within 1 standard deviation, somebody did that calculus for us, and we know on all normal curves, on every normal distribution, the amount of our area is 68%. Because of that, when I ask you about probability, what's the probability I hit that area? Or if I've got a bunch of data and that's the shape of my distribution of the data, what's the probability I grab a data piece from there? Since probability and area are related, I know that that probability is 68%. That something is between here and there. So 68% of my data is going to be within 1 standard deviation from the mean. Okay, then they kept doing more with the calculus, and they did the area out 2 standard deviations. So they found this area under my curve. And the area under that, from 2 standard deviations out, is 0.95, or 95%. Now, Chebyshev said at least 75%. But now that we have the normal curve, we know even more specifically. We know that in a normal curve, in a normal distribution, 95% of our data is going to be within that. Or the probability that I get something between those two distances is going to be 95% of the time. If I went out 3 standard deviations, so if I went out a whole nother one, and I found the area there, 3 standard deviations, that area is 0.997, or 99.7% of my data is going to be within 3 standard deviations from the mean. Now notice there's still a little bit out here. This thing keeps going. It never quite reaches 0, but it keeps going. So there could be some data out here. There could be some data out there, but that's only 0.3% of the curve is going to be out here on the outsides of it. Okay, we call this the empirical rule. The empirical rule says or maybe some people call it the 68, 95, 99.7 rule, because 68% of your data is going to be within one standard deviation, 95% within two, and 99.7% within 3 standard deviations when I have a normal curve. Okay, let me tell you more about the normal curve, and then we'll start practicing with this. So in the past, we've dealt with discrete distributions. So you know, when we did a binomial and we did that hypergeometric, we had a discrete number of things that we were doing, a discrete number of roles, or a discrete number of people. So we could count our variables. So when we made our probability distribution before, our x values were countable. You know, it was 1, 2, 3, 4. They were countable items. Well, in a normal distribution, our variable is continuous. So in a normal distribution, the variable is continuous. So think weight, think height, I don't know, ounces. Remember all those that we talked about at the beginning of the semester that were continuous? So that's what I'm dealing with, is a continuous variable here. So if so I can get my data can be close together, or can be more and more specifically measured. That continuous data. What else do you need to know about the normal curve? Let's see how I remind myself. The normal curve is symmetric. This is going to play a big part in it here in a minute as we play with it. What else do you need to know about the normal curve? Maybe I've already told you everything. Depends on the standard deviation and the mean. Asymptotic, I think I've told you everything. Okay, so now we're going to play a little bit with this empirical rule. Oh, I know what else I need to tell you. So it's dependent upon the standard deviation and the mean. So the notation for normal, remember notation just means the way we write things. The notation, we write an n, which means I'm dealing with a normal distribution, and then I put my mean and my standard deviation. Because my shape is always going to kind of look like this, but it's dependent upon that standard deviation and that mean. So I'm always going to put my mean and my standard deviation. So for instance, maybe I've got a curve that is, well in that case, I don't know, 0. The mean was 0 and my standard deviation was 1. Because my mean was at 0 and my standard deviation I counted by ones. But maybe instead I want to do a normal distribution. Maybe in my data the mean is 15 and the standard deviation is 2. So how does it differ? Well, this would be the same shape. It would be the same shape, but my mean now is 15. And if my standard deviation is 2, then that means I'm going to count out 2 spots. So, 15, the distance 2 away from 15 is 17. So that's 1 standard deviation from the mean. Or do you remember when we talked about z-scores? The z-score of that is 1 because it's 1 standard deviation above the mean. Then my next one up, 2 standard deviations, would be up 19. And then 3 standard deviations up would be 21. So the z-score here is 2 because we're 2 standard deviations above the mean. And then this z-score would be 3 because I'm 3 standard deviations above the mean. Going backwards, I'm at 13, backwards, and I'm at 11, back 2 more, and I'm at 9. And remember those z-scores? Maybe you remember doing those. This is 1 below the mean, this is 2 below the mean, and this is 3 below the mean. Okay, so let me ask you this. Based upon the empirical rule, between what two numbers on that distribution, if I have a normal with a 15 and a 2, between what two numbers lies 68% of the data? Oh yeah, I might should have been more specific. Mr. Simpson's exactly right. He's giving you some examples of the normal distribution, things that distribute normally. That if I were to gather the data, this is how it works out. Things like our heights, women's heights, men's heights, work out to be symmetric. Most women are here, and then there's some that are shorter, some that are taller, and it kind of works out that direction. The wing length of butterflies, most of them have this wing length and then it works out symmetrically. So there's a lot of things in biology and just out in the real world that turn out to be this bell curve. Good, guys. So between 13 and 17 is 68% of the data. So I could ask this question. I could say, what is the probability that, I don't know what that data is, but what is the probability that if I randomly choose a piece of data, between 13 and 17. So what is that probability between 13 and 17? You just told me that that was 68% of the data, so it turns out that that probability is 68%. Good, y'all got that. That is 68%. So you see how that works. Because that area and that probability are related to one another. Okay? How about I ask you this? Let me make it a little trickier. Y'all got this? 68, 95, 99.7. I'm going to erase my pretty little curve. Just the area for a minute. And I want to know about, I'm going to ask you about this. What is the probability that if I randomly select a piece of data, I get above 50? So greater than 15. That's a 15. That's a 15. What's the probability I get above 15? Yes, it is more precise than Chebyshev's because this shape, we can actually, because it's this function, this probability density function, I know I can actually find the area underneath it. It's exactly right. So we like things that are normal because then we can tell you with more precision exactly what that probability is. So I'm going to color where it is that it's above 15, and y'all see if you can figure out what this area is. of my distribution. Use your calculus knowledge. Yeah, good, Eve. It's 50%. That's exactly right. Half of my distribution, look at you using calculus. You just did some integration and found out the area under that curve was 50%. It was 0.5. It's half of it. Half of it is colored that direction. So then, what if I asked you what's the probability I get a piece of data below 15? What would that be? So below 15 is this direction. So what's that probability? 50%. So this is 50% and that's 50%. Sometimes we're going to use that to help us when we're finding the probabilities. Knowing that above your mean is 50% of your data and below your mean is 50% of your data is going to be really, really handy. Y'all have totally got this. Okay, so now let me ask you, I'm going to make it a little bit harder, and then we'll draw another one and see if we can do some questions from it. What about if I wanted to do between, what's the probability that I get a piece of data, but randomly, if I'm randomly choosing one, between 13 and 15? Ooh, that's hard. So let me draw where that is, in case you're having trouble seeing the numbers. What about that one? What do you think that one is? Between 13 and 15. Use that calculus knowledge of yours. Look at you, Bo. How'd you come up with that? Tell me why. See, y'all are already doing calculus. Look, Mr. Simpson, they're finding the area underneath this curve. Huh, yeah. Half of the 68. If this was 68% and these two are symmetric so that this half is the same as that half, I can cut this in half so that this is 34% and that's 34%. So notice all the way out to here is 68%. But this piece is the same as that, so I can cut it in half. So that one is 34%. Geniuses. Geniuses. I know. We need to get them in college algebra this summer. They need to take me for college algebra this summer. And then in the fall they can take, well, pre-cal somewhere. And then calculus. They're ready. They're already ready. All right, let's draw another normal. I've kind of abused that one. Plus, it's just good practice to draw one. So let's say I've got a normal distribution, and I say something like, I don't know, so what's my mean there? So my mean is that first number. The mean is the 9. That's where I'm going to start when I get ready to draw it. And then my standard deviation is 1/2. Good, good, good. So I'm going to count by 1/2. You know, whatever that distance is, keep it the same, keep it the same. Go backwards, go backwards, go backwards. Now, trick to drawing it. So I'm at 9 1/2, 10, 10 1/2, 8 1/2, 8, 7 1/2. And we know this thing is symmetric. So we know that the topmost point is going to be here at 9. That's where our mean, our median, and our mode are. Excellent, excellent, excellent. That's exactly it. You're right. Then here, it's coming down, and this point and that point are going to be at the same level. They're going to be about the same. Well, we know that it's symmetric, so it should fold here and match. So, the top part looks like this, kind of. I always have to stand straight in front of it to get it. Then we call this point an inflection point. For those of you who did that exponential bonus, you've heard this word inflection point before. And maybe you remember that inflection point is where the concavity changes. So it's curving one way and then it's going to curve the other way. We're all waiting around for our inflection point right now with this coronavirus, because right now it's exponentially growing, but when we hit that inflection point, then that tells us it's going to start to, the curve is going to change, it's going to start to flatten out. So that inflection point is what we're all kind of waiting around for. Then I'm going to put another spot at my next standard deviation out, so that it changes its direction here and it's coming down. Again, those are symmetric, and we're getting closer and closer to that line, but we never reach it. And my distribution keeps going out there, getting closer and closer to 0, but never reaching it. I will encourage you, and on some of them tonight I tell you to draw the normal. You really want to draw the normal every time. And then you want to color in that area. It really will help you to see. If you color in the area that you're looking for, it really will help you to find the probabilities. So the people who do that, draw their normal curve every time, color it in every time, are always more successful at finding probabilities. And those who don't, then they usually struggle with this. So don't hesitate to draw the curve and color it in so that you can see exactly what you're looking for. Okay, so then what if I ask you, what is the probability we get between probability between 8 and 10? Or remember, in our notation, we've been doing the probability. And this, to say between 8 and 10, I would put my x between my 8 and my 10. So between, my x is between 8 and 10. Yeah, so that's how, I'm going to color it in to show you. 8 and 10. So I'm looking for this area under that curve. And you're right, it's 95%. That's the probability that I get it, is 95%. Because by the 2SD rule, by the empirical rule, out 2 standard deviations is 95% of my data, or 95% probability, or 95% area under the curve. All right, what about if I change this, and instead of saying from 8 to 10, I say from 9 to 10. So this one was 95%. What if I change it to be from 9 to 10? So the probability between 9 and 10. So think about what that looks like. I'm going to go from 9 to 10. Good, Lucas. Because all I did was take and split that in half. I took my 95% and I split it in half to get that 47.5%. Excellent work. Excellent, excellent, excellent. Great job. That's right. It's all calculus is. Nothing to it. They make it sound hard, but really. Okay, now I'm going to make this a little trickier. Let's see. First, I have a normal that's, let's say 10 and 5. And I want to know what is the probability that we get some value between, or let's do it this way, greater than 5. That one's tricky. It's going to be a little trickier. Okay, I'm going to always encourage you first to draw your normal distribution. So the first thing I'm going to do is I'm going to draw it. I'm going to put my mean in the middle. And this is a bad standard deviation, but we're going to go out 5 each time. I'm going to go back 5 each time. And somehow or another my data is in the negatives. Okay, whatever. That's okay. Somehow my data is. Oh, wow, Lucas is already on top of it. Be ready to tell me how you know that or why you think that. All right, now I'm going from 5. So I'm going from 5 here. And I'm going greater than that. Yeah, it really helps if you draw it out first so that you can see it. But you got, so Amadi, you know from where out is 50%. How'd you get it, Lucas? Tell us how you did it. Or why you think that. Yeah, drawing it out really, really helps. Let me help with this first. What is it from 10 out? You told me that one earlier. If we just ignore this piece for a minute, what is it from 10 out? How much is that? So ignore that piece for a minute. How much is it from 10 out? So from here out to there, forever and ever. Good, that's 50%. So you know that this piece is 50%. Above the mean is 50%. Perfect. Then what about between this 5 and the 10? How much did we say was between 5 and 10? I feel like we did a piece like this earlier. How much of our data was in there between that 5 and that 10? There you go, 34%. Good. Because this piece right here is half of that piece. You know, this was one standard deviation out is 68%. So this piece is just going to be 34%. You got it. So you got this 34% plus that 50% is going to make a total, 34% plus 50% is going to make a total of 84%. So the probability that I get something greater than 5 is going to be 84% of the time. 84% of the time. But yes, drawing it out is really going to help you. And then you're going to use that empirical rule, you know, knowing that this is 68%, knowing that this is 95%, knowing that this is 99.7%. And then also you're going to use this 50% above and this 50% below to help you out. Those are going to be handy. Let's do a couple more. It's kind of tricky to get your mind wrapped around it. And some of it's a bit of a puzzle, so you're going to have to really stop and think about what can I use? Which one of those empirical rules can I use? You know, is it the 1SD? Am I using 1SD? Am I using 2SD? What am I using? All right. That's worthless. We'll pick a different number, a bigger number this time. How about like 55? And we'll count by threes. So y'all start by drawing it out, and then I'm going to ask you, what is the probability that we get from 46 to 64? Oh, that was smart, Lucas. Get a jump ahead. Smart. Pure genius. Tomorrow is all we do. You can probably do tomorrow's too, or tonight, the normal one also, because it's the same thing only with words. I just add scenarios. So tomorrow we'll talk about how we use this in the real world. Like Mr. Simpson was saying with biological things like heights or IQ scores. And then how does that relate to policy that's implemented? How do we actually use this information? And the normal curve is so important in statistics. Turns out to be like super important, this idea of normal. Everything that not everything, but a lot of the statistical things that we decide on is all based upon this normal curve. A lot of it is. Okay, I'm going to go ahead and draw it. So I got 55. It always takes me forever to draw it because I'm too particular. 61, 64, backwards, 52, 49, 46. My inflection points, then it curves around. So from 46 to 64, what is it? Yeah, 99.7. Good, Aunt Kara. Okay, now, so this is 99.7. Perfect. Okay, now let's do the probability from 46 to 55. What's the probability that I get from 46 to 55? So in other words, I'm doing this piece right here. What's this area under the curve? Or what's the probability I get a piece of data out of there randomly? It would be 50 if I said below 55. But notice this keeps going. I could get values down here. Not very many. There aren't very many down here. But there are some. So it's not quite 50 because 50 would be anything below 55. But I cut it off at 46. So it ends up just being half of that. Half of that. So it's almost 50% because this is almost almost 100, but it's not quite. Instead, it is that 49.85%. If you cut this in half, so there's still some out here. 0.15% is way out there. Not very much of it, but there is this possibility. Okay, let me make it a little trickier. Let me ask you this. How about if we do the probability that I get that x is below 52 or greater than 58. So let me draw that to show you what I'm dealing with. So I want to know what's the probability I get that or that. In other words, what is the area under the curve here shaded? How much of it is shaded there? What's the probability? How much of my data is going to be below 52 or above 58? It's a little bit trickier. Can you figure that one out? Tell me why you think that. Tell me why, tell me why. Tell me why, tell me why. Tell me why, tell me why. How y'all getting that? So if we were stopping it at 46 and 64, you're right, that would be 99.7%, and you would subtract off that 68%. But it is, all of it makes up 100. So we're actually going out for, this didn't stop us. We said below that 52 and above that 58. So the whole thing, if I colored in the whole thing, it would be 100%. I'm subtracting off the 68%. So y'all all had the right idea. That was all the right idea. You take that 100 and subtract off the 68, and that gives us 32. So 100% minus 68% gives me 32%. Or, the area is 1 minus that 0.68 equals 0.32. These numbers are the same numbers. Those things are the same. So that was good thinking. You had the right idea. And Amani's right. If I do it above and below, then it makes up the whole 100%. If I cut it off, then you're looking for that 99 or 95. But good job. Y'all got this. Okay, let's see if I can make it a little bit harder, and then we'll let y'all go practice it. What if I do... By the way, before I make it harder, what if I did this? What if I just said, what's the probability that x is greater than 58? So in other words, not this part, just that part. What's the probability that it's greater than 58? And why? I like it, Lucas. Sounds good. Tell me why. Tell me why. Tell me why. How do you know? Lucas claims it's 16%. I mean, we know it would be less than 32%. If this is 32%, that's got to be less than it. Why would it be 16%? Where would he be getting that 16? Sure doesn't look that way on my picture, but yes, 16%. Yeah, because this half should be equal to that half. If my picture was, halfway right, if this half is the same, if I fold it, these two would match up. So I can take the 32 that I had there and split it in half to get that 16%. Y'all have got this. So the whole idea tonight is going to be to play with that empirical rule to be able to find things like that. They may be a little tricky at first to figure out how am I going to come up with that. Let's see if I can think of a hard one. What's the probability that I get... Oh, we'll do a really hard one. What's the probability that I get from 58 to 61? Now that one's tricky. We'll end it on that one. If you can do that one, you can do any of them. I'm going to draw it out again so I can color it in. Horrid at drawing this thing. Okay, so from 58 to 61. So just that piece right there. That's tricky. Y'all do. Y'all need some sort of avatar. Some picture on there. You just pick something and upload it. Get you an avatar. That's pretty tricky. See if you can come up with that. I'll help you out a little bit. I'll lead you to it. I'll lead you to it. Lucas says 8. Let's see. I don't know. It could be. I'll lead you to it. I'll do it in baby steps. First, although I may do it a completely different way than you. There are lots of different ways to do it. So I'm going to start this way. Mr. Simpson might do it a different way. Lucas might do it a different way. So we might all do it a different way. But if I go from 49 to 61, what would that percent be? So let's just start there. What's 49 to 61? So I always try to look at my empirical rule. I know 1 SD, 2 SD, 3 SD. I know that rule. So I try to start there. Or I start with the mean. If I can use half of it, if it keeps going one way or the other, then if it does this, then I start looking at that 50% this way and 50% that way. So I start thinking of it that way. Good, Lucas. So this part's 95%. Okay, now I'm going to look at, let's look at half of that. So if I just go from here to there, that would be half of it. So, I don't want that whole thing. I wasn't doing this side of it. I'm only doing this side of it. So if I just look at this half of that 95%, y'all figured that out earlier. So to go from 55 to 61, you know that that one is good, 47.5%. Okay, so I know this piece is 47.5, but somehow or another I need to get rid of that piece. So to figure out that piece, well, that's one standard deviation out. So I know if I do the whole standard deviation from here to there, that one's going to be from the 1 SD rule, from the 1 standard deviation out. I know this whole thing is 68%, but I'm cutting that in half. So what's this piece right here that I want to cut off? It's this whole 47.5, but I want to get rid of this piece. So how much is that piece right there? Good, that one's 34%. So I know this whole thing is 47.5, but I want to get rid of that 34%. So I'm going to take the 47.5, this piece right here, cut off that 34%, and that should leave me with this piece. 13.5, that sounds good. 13.5, I think it's 13.5, let's see. 3, yeah, 0.5, 13.5. Okay, now you see that was kind of tricky. So when you get a piece, the first step is to draw that normal curve and go ahead and color it. And then start labeling pieces that you know. I know that this part's 95%, but I don't really care about that half. I'm going to cut it in half, and this is 47.5. You're going to have to do a little puzzle work in order to figure it out. But I think this is about as hard as it gets. There's not going to be anything harder than that tonight. So you can do this. Go play with it. Draw your normal. Figure out the pieces that you know, and then subtract off if you need to. But I think tonight's is a little easier than that. And then tomorrow we'll add scenarios to it. How do we use this stuff? Why do we use this stuff? What is this? That's right. Definitely need some markers. Pull out your crayon, start coloring. It's not bad. That's what math really is. And I'll be on Discord, so I will be here to help. All right, I'll see you there, and then I'll see you tomorrow at this time. It's not too bad. It's not too bad. That's as hard as it's going to get. It's going to be all right. It's going to be all right. It's going to be all right. And I'll see you on Discord in just a minute. Oh, Math Made Simple. It's Simpson Math. Thanks for watching. Almost forgot my sign off.